So today we have a goal to introduce, this is one of the two lectures, introduce you about how the exception handling is done in your platform. Okay? And your program assignment 1 will be you will be coming up with writing a small utility functions that you can carry from platform to platforms that you know how exception is handled. Okay? This is important for writing any robust code that you need to know, right? How when a exception in computation happens, what happened, okay? So that the in any platform, and this is many times platform dependent, okay? So that's why this is a good topic to introduce to start, and also a important thing for you to learn, okay? The first and easiest exception handling is something I don't know how many times you have seen in your computation. And when something goes wrong, all your output is NaN. Okay, maybe you have done anything that's slightly serious, you should see this. Okay, this is called not a number. Okay, and in double precisions, there's a special code word in the IEEE 754 standards when the exponent is equal to 01, the exponent field. Okay, remember you have a sign field, mantissa field, and exponent field, right, for any floating point. When the exponent field is 01, that's reserved for the exception case for NaN and infinity. Okay, not a number is when the exponent is 01 and the mantissa is not 0. Okay, sign bit doesn't matter, but the standard doesn't tell you what the mantissa should be. It just tells you it shouldn't be 0. Okay, so that allows the platform to implement many different types of not a number, okay, for further handling. But the regulation says, okay, if your exponent field is 01 and the mantissa is not 0, it signals a not a number, okay, signal not a number, and it will many times generate a exception, okay, exception flag. Okay, you will do the practice today how this is handled on your platform. Okay, so how not a number is generated? These are the typical rule. Okay, we'll tell you about the infinite immediately. Okay, when you have infinite minus infinite, the program doesn't know what it is, or infinite plus negative infinite, the program don't know what it is. For sure, infinite plus infinite will be infinite. Okay, that's something actually is known, right? So this is from the addition and subtraction rules. You can produce an NaN by such exceptions. 0 times infinity, for sure, it's not a number because it doesn't know what it is. Okay, it's not 0. Okay, it's a division rule can be caused by 0 divided by 0, infinite divided by infinite, or infinite divided by negative infinite. Okay, so these are the will give you all the not a number. Okay, not a number, and for sure there are other cases when the remnant functions or the square root it doesn't know what to do. Okay, then it will return not a number. Okay, return not a number. Okay, for sure if you look at these cases, if you're dealing with the symbolic form, there are further things you can do. Okay, that's left to the programmers, right? You probably, hopefully you remember in your calculus, there's something called the L'Hopital's rule. Okay, that when the both the numerator and the denominator go to 0 or infinity, you can do more things by differentiations to get more information. Okay, more information by the L'Hopital rule, but that's symbolic. Okay, numerically it's not provided to you. If you want to implement L'Hopital rule, check this exception and then do things symbolically, and that's the programmer's responsibility. The program won't handle it for you. Okay, it's the programmer's responsibility to do that. Okay, I'll show you example at the end how that can be done. Okay. And exception handling for not a number, it really propagate. Okay, so anything that any operation that meets another number, it will propagate for another number. And usually, depending on your platform, there will be environmental variable be set. Okay, in the Unix system or Linux systems, it's SIG FPE, meaning that this is signaling a floating point exception. Okay, that environmental variable will be set. And in C++ language, additionally, there's something called throw and catch operations. Okay, what does it mean? In a modular programs, right, it's executed hierarchically. When you have an exception or when you have an interrupt, something have to break the hierarchy, right? If you want to catch that, right? So if you have, say, one program calling program 2, program 1, calling program 2, calling program 3, and here a FPE floating F signal, sorry, signal FPE has been set, right? If you just catch it here, it's not sufficient, okay? So this one will throw a exception and be able to be caught by the top program. Okay, so this is something some of your programming classes may have introduced to you, how exception flags are handled within a hierarchical programming. Okay, this is actually, I checked, this is program assignment 2 in our CS2 2110. Okay, how to catch an exception being thrown. Okay, but again, this is platform dependent. Okay, may not be handled this way, but the programmer need to know that what may happen. Okay, the programmer needs to know what may happen when something like this, when a exception has been generated. Okay, so. Okay. So now, this is floating point. Okay, at least usually the platform is doing something for you. Okay, in integers, which we are going to do the experiment. Okay, integers are good in one way. Integers are exact, right? There's no precision issue in integers. When you say 1 or 2 or 3 as integers, they carry the idea of infinite precision. Integer does not have errors. Okay, it's just the way that we perceive integers. Okay, when I say 1 apple, it doesn't carry an error of 1.0001 apple. That concept doesn't exist. Okay, and this is exactly the reason of why digital as an integer is so great. Because if only some numbers are allowed, you can use them to do error correction. Okay, so this is integer have this built-in concept in there. When I say 1, it means 1 with infinite precision. When I say 3, it means 3 with infinite precisions. Okay, that said, that also means, right, that's when you convert from floating point to integers, the precisions built in the floating point need to be handled somehow, right? So in C and Python, actually, most of the time it's by truncation. Okay, it's an experiment you can do in Python or C. Okay, your integers equals to 5/3. It will, when you return I, it will give you 1, not 2. Okay, because all the numbers are truncated. Okay, all the number below the integer is truncated. Some MATLAB give you a round off, 0.5 round off rule. Okay, return a 2. Okay, so this is something that you need to know as a programmer. What will happen? Okay, this is something that's integer and like this. Okay, integer can easily overflow. Okay, just try to calculate a 13 factorial. Okay, your 32 integers will overflow. Okay, now it's the punchline. Okay, integers in the IEEE standards do not handle exceptions. Okay, there's no concept in integers of not a number or infinite, okay, or negative infinite. Integers are simply integers. They don't handle exceptions. Okay? And when you go for conversion of integers, again, the platform dependent, if you assign an integer to not a number, nobody knows what will go on. Okay? It's really platform independent, platform dependent. Because in the 32 bits of integers, it doesn't reserve any number to be signaling the exceptions. Okay? So when you program in integers, okay, just be careful because there's no exception handling. All exception handling in integers is the programmer's responsibility. Okay? Floating point, there will be rules and things, underflow, gradual underflow, infinite, not the number, handle some exception for you. In integers, no exception handling. There's no reserved word for exceptions. Okay, we'll do the experiments at the end of these lectures. Let you see what happens. Okay, what happens. And you may say now, but 32 bits is pretty big. Okay, it's not big at all. Okay, most of the cryptography, right, require calculation of integers about 4,000 bits. Okay, so handling large integers is the number one word in cryptography. Okay, again, is something that the programmers are required to operate in the integer domain, but not represented by the platform integers. You have to do your own binary. You have to do something special. Okay, because it's not handled. In your platform, they don't handle the 4,000 bits integers naturally. And this is right? Because if they handle it, and for these such long and large integers, if any integer can be that large, then your program will run slow like hell, right? So it's a trade-off between how many bits for in integers, and when you really need to do something special, then the programmer's responsibility to do that, not the programs. Okay, not the compiler or your language won't do that for you. Okay, so some magical things can happen. I won't say it's magical. Magical is a good word. Some strange things can happen. Okay, try it. Okay, we'll try very soon about how integer can overflow by calculating factorial. Okay, and your platform may surprise you. Okay, as I said, it doesn't reserve a representation for exceptions. So what will happen? We'll see. Okay, many times in generic C compiler, when you calculate 13 factorial, which is not strange, right? Many of the computation may come with a 13 factorial. It will return to you a negative number. Okay, let me see if you can see that. Okay, something strange. Okay. So, is this the computer problem? Okay. Let's see what is the best strategy. Okay, if I have an integer 1 divided by integer 0. Okay, what should happen? Okay, now you are the person who is going to develop the new Python, maybe the big snake or something. Okay, a new language. What will you do? Okay, what will you do? Okay, so I say 4. Okay, feel free to come up with the fifth option. Okay, I say if I implement the language, and if the programmer have an operation, many times not intentional. Okay. But 1 divided by 0, both integers, I can give the largest integer because I guess the programmer must mean something very big. Okay. Second, what thing I can do? I will reserve a symbol in integers like the one I do for floating point. Okay. Maybe just all the binary number is 1. I reserve that for a symbol and signal the exception. Okay, second possibility. Third possibility, I'll internally change that integer representation to floating point and signal the infinity, because infinity is reserved in floating point. Right? Fourth, I don't do anything. Okay? Now, going back to your experience in programming. If now I allow you the freedom to choose the language features, which one will you choose? Okay, I'll give you 30 seconds to talk to your neighbor, and then we'll vote on the 4, okay? Which one will be a good strategy? Or you can come up with a 5th strategy if you want to, okay?
Yeah, exactly. I lean towards 3 though. Yeah. Just like don't most like just like regulate division by 0. Yeah.
Okay, with a very short discussions, let's vote. How many of you, let's do individual vote instead of group vote, okay? How many people think that the first strategy that you give the largest integer when you encounter 1 divided by 0? How many people this is the right strategy? 0? Oh. How about the second? Reserve a symbol in integers. I get 3, 4, okay? 3 is change to floating point and rapid signaling, okay? 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. 4 is do nothing, do not regulate it. 1, just 1. Okay, 1, okay? Any other suggestions how it can be handled?
Can we just signal an exception, like do nothing else?
Signal exception.
Yeah.
You mean throw a environmental variable, okay?
Yeah.
Just throw, okay? But what do you reserve as say x is equal, m is equal to 1 divided by 0? What do you do with that m?
Oh, but like wouldn't the program just like not function unless you catch the exception?
Yeah, but what do you assign this?
I don't know. I guess then 3 is fine then.
Okay. So you will add 1 more 3 point, okay?
No, I'll do it.
Just throw, okay? That's that, okay? Any other? Have you? Any comments?
No, I just tried.
Yeah, okay.
And I would say
You just try it and then what?
like it just gives me an error. So
Okay, so this one compiler will catch. Okay, so this is not fair. Okay, more compilers will tell you, oh, this is not allowed. Your integers 0 cannot happen here. Okay, usually you have to do something like this, and then do I divided by j. Then the compiler won't catch it. Okay. The compiler is reasonably smart to catch your direct 1 over by 0, okay? So you have to assign a variable, make it to be 0, and then divide. The compiler won't catch it, okay? Okay. Oh, we'll do that exercise immediately here. So you see this, okay, your vote, okay? Giving the largest integer is very dangerous because you will make many of the operations to be very strange, right? Like when that happened and when that things continue to +1 or do something, right? That you assign the largest integer, then that largest integer, how about that largest integer minus 10? What are you going to do? Okay, you give a largest integer minus 10 is not the original computation, right? And your computation can be totally order dependent, right? Because once you met overflow, you assign a large number, right? But if you change the order of computation, you come up with a different number, right? So 1 is actually very dangerous. Nobody choose it. This is good, okay? Second is reserve a symbol to signal the exceptions, okay? This is possible, okay? But make integers operation rather slow. Okay, many of the factorization, parallelizations, when your program use this integer to direct traffic, okay, it's not a computation. Okay, you have an integer to do direct traffic, and every time you have to check that, okay, for exception, it's very difficult for you make it to be very fast. Okay, so integer, you remember your first assignment maybe integer for 100 loop, right? That I for the loop variable many times doesn't mean anything. You just want to do something 100 times. And that 100 times is golden opportunity for the compiler to do factorization and parallelization to make it much faster. But each time I have to check, is there an exception? Is there an exception? Okay, then it's a very inefficient way for handling integers. So this is usually not done. Okay. Third, the popular choice is most dangerous. Okay, implicit type conversion is almost that in any programming language. Okay, is something that they warned you. Okay, some language allow you to do that implicit change in the data representation. The user didn't even know about it, but it's changed. Okay, is one of the most dangerous thing to do. Okay, strong typing, weak typing, right? Even weak typing is allowed. It will tell you the warning. Okay, when implicit type conversion is a very dangerous thing to do, which it is, right? Remember, if I declare an I, and after some computation, it becomes a floating point without your control. It's very bad. Okay, so this is not popular. Okay. 4 is actually most of the language do that. Since it's too hard, I want to maintain the efficiency. Let me don't do anything about it. And the user, whatever you want to do, you check it. I don't do the implicit check for efficiency's sake, and I don't do anything funny that cause even more danger. Okay, well, go for that. Okay, just throw. Okay, maybe something that I don't know if any language do this. Okay. It's a possible thing to do, but just throw, meaning that for that variable you do nothing about it. Okay, close to the 4. Okay, so the next one is overflowing in floating point. Okay, the infinite. Okay, let's see how infinite. Now we know the caveats in or the number and integers. Infinite is actually handled in a reasonable way. Okay, so we reserve a symbol for infinite. Okay, remember this is not the maximum double. Okay, maximum double is usually double max, or in your language many times is a reserved environmental variable. Okay, as long as you in C or in C++, if you have math.h, okay, you include the header file. Okay, then the double max and a double negative max is already reserved, defined. Okay, defined. Okay, infinite is not double max. Okay, infinite is a special case when exponent is 1 and mantissa is 0. Okay, when mantissa is not 0 and the exponent is 1, it's not a number. Okay, and when exponent is 1 and the mantissa is 0, sign bit 0, infinite. Sign bit 1, negative infinite. Okay, just the way it is handled. Okay, let me give you this example to illustrate why this is good. Okay, so if you compute a simple things like the Pythagorean number, okay, so that number you actually know it should be 3 times 10 to the 160. Right? For any, it's a something right and representable. Okay, and you may encounter such computation, right? Pretty often. Okay, but if you x squared will overflow, right? So if you have x squared to be double max, the answer will be 0. Right? Look at the execution, right? If x is large, x squared will overflow, and when you handle overflow, instead of reserve a special symbol, you just switched it with double max, then the answer will be 0. Okay? These things can happen in integer as well. That's why the first choice, right, substituting an overflow with a large number is dangerous. Okay? Because in the series of operation, you may come up with something that's totally unexpected. Okay? But if you handle by the infinite, right, by a special symbol, x squared is infinite, y squared is infinite. Infinite minus infinite is not a number. The square root of another number is not a number. Even though your precision do not allow you to calculate the correct value, at least the programmer will know something is wrong. Okay, so it's not the ideal way. There's no perfect way to do with it. So this is the many language choose to implement in such way. Okay, use infinite and use the rule to propagate infinite and not a number to handle such cases. Okay, good example to do. Okay, so infinite rules is something like this. Okay, these are infinite rules. Okay, infinite 1 divided by infinite is 0. 0 divided by infinite is 0. Minus 1 divided by 0 is negative infinite. Okay, we will talk about the positive 0 and negative 0 in the next lecture. Okay, so there's once you introduce the idea of infinite, there is an issue. When this 1 over infinite of this 0, whether this a positive 0 or 1 divided by negative infinite is a Dewey symbol, a negative 0. Okay, I'll talk about sign zeros, okay, in the next lecture, okay? But just now, handle the infinite in this way, okay? Okay. And for sure, then infinite is, as I said before, if you do not know what can be the asymptotic limit, then this is what you do, okay? You're going to do, okay? And you can do better if you have existing knowledge, okay? If I have existing knowledge to check bounds and things, you can do better. But it's the programmer's responsibility, not the platform responsibility. Okay? So, overflow exception, even with the present implementation, can still be problematic. Okay? Let me give you an example. And this is not a strange thing, okay? Not a strange thing that is a strange computation you may never encounter, okay? You look at the formula of a function, okay? And this is equivalent to this function, okay? This is some function that you probably see, right? That you do the x plus its inverse, okay? It's not a strange function, okay? Many of the approximation functions will give you this. Well, this will make, right, cover the small, when it's large, it's large. When it's very small, it's also very large, okay? So this is functions that's frequently encountered, okay? So if I give a very large number, okay, 2x, about square root of the largest number that it can carry, if you do that evaluation, okay, the evaluations of containing an x squared, where x squared will overflow so become an infinite. Anything plus infinite is infinite. Any finite number divided by infinite is any finite number divided by infinite is a number, right? Finite number divided by infinite is 0. It's not a number, right? Infinite divided by infinite is not a number, right? But the rule handle any finite number divided by infinite is 0, right? So this will actually, for that expression, it will give you 0. Okay? But a totally symbolically equivalent number of this, okay, it will give you something that's correct, right? Because there's no overflow, what happened, right? And if you give a very large number, and the answer actually can be correct. Okay, so this remains to be the programmer's responsibility. Okay, your platform don't handle it for you. Okay, so we do something, but it's still useful. Okay, still very useful. Okay, so whenever infinite is generated, okay. you can do something about it. Okay, you can check in infinite, but the platform don't check it for you. Okay, any check break the chance that the program can be more efficient. Okay, so usually that the programmer need to know what is the most computational expensive step. Okay, and don't check it. Okay, for unnecessary check, because a check in an if statement, two possible outcomes break the chance to go parallel, right? The way that you can do parallel factorization, right, is that I can execute, generate more symbols, right, to execute in parallel. When you have an if, then you have to wait for the if statement to be executed, then you can do things again, right? So if statement, your check is reserved that the platform don't check it for you, okay? It's your responsibility to check, okay? And is the trade-off of the efficiency and safety is the programmer's responsibility, not the platform responsibility. Okay? So now let's do the schedule platform, and let's try these three things, how it is handled, okay? So the first one is how your not a number and infinite is handled in floating point. Second is in integers. Okay, I just mentioned you cannot do 1 divided by 0 directly, okay, because that will give you a direct compiler error, okay, if it generates that. Okay, please try this, okay? And let's see how your, the third one is how your overflow is handled in integers, okay? Let's program this, okay? If you do in Java, this will be Java or Python. This will much more reduced. Okay, feel free to do in Python. Okay, Python for sure has only float, does not have something called double. Okay, and you don't even have to say it. You just have to assign a number. Okay, and the Python will assign the type for you. Just remember, it's 1.0 for floating point. 1 will be an integer. Okay. And feel free to do in MATLAB or whatever, okay, please. The more diversity you do, the more observation I can have, okay, how these things, very simple program, is handled differently in different platforms. For sure, this is pseudocode, okay? Print is not even defined in C++. So do some substitution reasonable that you can observe, okay? These are pseudocodes. If you finish, you can look at me, then I know you finished. Yeah, feel free to ping into other solutions. This is not a test, okay? Something, but if you have results, compare with your neighbors. It's totally allowed. If you finish and have nothing to do, I'll give you something in addition, okay? How do you check a number is not a number? Okay, I didn't hear a lot of clicks of a keyboard. Okay, let me pull that what are your observations. Just I'll pull it, okay? So if your answer is just the same as other people, you don't have to say it again, okay? But let's please verbalize your answer, okay? About the first one, in generating the another number in infinite, what do you get for double result 1, which is 1 divided by 0 in floating point? What do you get? What?
Zero division error. Zero division error.
Zero division error. So you see an error. Okay. That's also something that's rather annoying many times, okay? Because if you stop execution, it's annoying, right? So Python actually stop execution entirely, so it doesn't let you, the user has to do something for it to continue, okay? So when you write a large number, or for you write a program for user to use, the user go out of your parameter space, and you just halt execution. Okay, many times it's annoying. Okay, any other answer?
Wait,
Yeah.
it's C++.
Yeah.
Inf and
Inf.
negative not a number. For double result 1 was inf,
In,
and double result
and your double result 2 is
negative not.
negative, not a number. Okay, so as I said, negative, not a number. The mantissa and sign bit is not regulated. Different platform will tell you what kind of not a number it is. Okay, so it's okay. Any other? Does anybody try this in MATLAB?
C++, infinity and not infinite.
Infinite and not a number. Infinite and negative not a number, or
Just not a number.
just not a number. Okay, so you see one difference in the platform. Okay, how not a number is different. Okay, it's not regulated. Okay, any other answers? So Python will halt exception. C will give you some handling. Okay, any MATLAB here?
MATLAB is infinite and not a number.
So MATLAB handle just like the C, okay? Actually, there is a program called M2C, okay? So most MATLAB can be converted to C code anyway, okay? So just that with MATLAB give you a lot more math library, okay? But there is, you can convert most of the MATLAB to C directly, okay? How about the second one, integers? What are the things you get?
I got a floating point exception.
Floating point exception.
Yeah, so, I might have.
All integers and give you floating point exceptions. Good. Well, then it's just throw, right? Good. Okay, your platform is no wonder it's you. Okay.
So
Anything else?
But Python is still called zero division error, but the expression is different. This time it says integer division of 0 multiplied by 0. Multiplied by 0.
Model 0, right? That's
Yeah.
divided. Okay. Yeah. Okay. So you halt execution. Any other answers? For how do you handle 1 divided by 0 in integers? There should be something else. No? That's it? Okay. So throw in exceptions and then do nothing about it. Okay. Interesting, huh? How about this one? Overflowing integers. What do you get? You should have an overflow after 13. Okay.
Python is not there.
What?
In Python there is no overflow.
But what it give you though?
The exact number. The 29 factorial is the last value.
How about the 14?
It's there.
How about 20?
About 29 and
21
Yeah.
becomes negative for me. But overall,
Okay.
it's a 21.
For me, after like giving right answer.
Okay, it has to have a bound, right? So when does it give you the wrong answer, right? 30 factorial is totally astronomical number, okay? So it's what is your factorial 30? Python give you correct integers? That means
Yes.
a very, very huge integers.
Yes.
Whoa, okay.
It might be because of how.
Can you invert that integer for me? Or even funny, divide it this one, okay? See how great is your Python, okay? If your 30 factorial is still correct, please return this for me, okay? And
So why was it getting?
What?
Why was it getting a floating point exception for the second
it's platform dependent. I don't know, right? Because it's not regulated. There's some platform give you negative number. I'm not kidding, right? A large factorial give you negative number. It's not regulated. It's the programmer's responsibility to do it, right? Because anything the platform do it for you can be hurting the efficiency of regular operation too much. So you just give the responsibility to the programmer. That's all that is. And you need to know, okay? That's all the purpose of this, okay?
In Python, it gives like a big number and then it ends with an L at the end.
And then what?
An L at the end.
L at the end.
Yeah.
Okay. Interesting. Can Python do this? For sure, I'll be greedy, okay? If this one give me 30, please add another 0 and another 9 here. I want to see where you break, right? Easy to break, right? You cannot be always correct. These have to break all computers, right? All languages.
Yeah, and then do efficiency.
And don't feel this is strange, right? A programmer that you have an independent variable, you have 300 choices, you're asking for the combinations of group of 5 within 300 combinations. You will do a 300 factorial directly.
C++ gives a -1 for that.
Okay, this one?
Yeah.
Okay, not strange, okay. As I said, it's the programmer's responsibility to check, right? And the platform can give you something really weird. What is my Python answer for that?
I mean,
If
if you use a math library
okay,
and then do factorial, it gives 30 for that.
okay. How about this?
It gives 300.
Whoa. Okay. How about 3,000 then? I'm greedy.
It gives 3,000.
You get 3,000. And he printed how, then I'm really interested in printed out 3,000 factorial then. That's about, how many digits is that? That's about
Yeah, it's a huge, huge number.
huge.
But it prints it out.
Ah, okay. Good, okay. What?
It gives me 30.
What is the word you say?
It gives me 30.
30,
For
okay.
the fact 1/5.
Okay. So what Python of that version must be doing is something called the dynamic bit locations, right? So the larger the number it is, I give more bits and throw it into it. Must be, okay? The penalty will be, there's no fixed allocation for an integer. Then it will be slow, right? During other type of calculation, okay? Well, okay, so good, okay? So Python actually do dynamic allocations. Okay,
For MATLAB, it's also 30.
how about 300? Maybe 30 is too, I'm too conservative. But you just tell me that even 3,000 factorial is correct in Python. Okay, that means it's pretty smart in doing the dynamic allocations. Right? But that probably will carry a penalty when those things are done. When that I is 3,000 factorial, you use say 4,000 bits to represent it, right? Any manipulation of that integer will just be hell, right? Yes? 300 is correct too, right? Okay, so Python. Okay, good. Okay, so these are something for you to think about. Okay, the Python do something that's dynamic allocations. That's giving away the efficiency concern. And Python is an interpretive language. Okay, probably that's why it has the luxury of giving the dynamic allocation. Okay, any other language, Java or C, I don't know if you have Java here. Okay, is meant for a compiled language. Then dynamic allocations for computation is not possible. Okay, way too much penalty. Okay. So tomorrow at night, I believe the room is also this one. I'll walk through your first assignment, okay, which is, as I mentioned, I want you to come up with the utility of how your platform handle the different cases. Okay, so I'll walk you through that. I'll also give you the first introductions of how to do modular programming. Okay, what should be separate to .h, what should be separate to library functions and things. I'll give you the first look about that. Okay, modular programming is not the goal. Okay, modular programming is a means to a goal. Okay, so you write very good modular programming. If you fail two purposes, you are still doing very poor programming. Okay, if your modular programming don't give you good test, every module can be very well tested. If you don't achieve that purpose, modular programming didn't bring you anything. The second is code reuse. Okay, if the modular you write is so special, it can be used only for your program, then you fail the point of modular programming. Okay, so this thing actually takes time to introduce. Okay, so I'll be able to gradually introduce you concept about how to do modular programming for the purposes of testing and the purpose of code reuse. Okay, so that'll be tomorrow night. Okay, that'll be it for today.